A new section, Monte Carlo. All of it rests on one primitive. Your computer hands you exactly one kind of randomness, a uniform number between 0 and 1. That is the entire supply. But you want exponentials, normals, whatever distribution the problem actually calls for. So the first question of the section is a manufacturing question. Given a uniform, how do you build a sample from any distribution you like? The answer is the cumulative distribution function, run backwards. Take the CDFF of the distribution you want, invert it, and feed it your uniform. X equals F inverse of U. That is the whole algorithm. The proof is 3 lines. The probability that X is at most little x is the probability that F inverse of U is at most little x. Because F is increasing, that is the probability that U is at most f of x. And U is uniform on 0 to 1, so that probability is simply f of x. Which is exactly the claim. X has CDFF. Notice what the argument needed. Only that f is a cumulative distribution function, and that we can invert it. Nothing whatsoever about the shape of the target. One uniform number goes in, one exact sample comes out, every single time. No rejections, no iteration, no tuning. Here's the same fact as a picture. Draw the CDF. It climbs from 0 up to 1. Your uniform U is a height, so drop it onto the vertical axis, slide across until you hit the curve, and read off the x underneath. That is your sample. Now scatter uniforms evenly up the vertical axis, evenly, because that is what uniform means, and watch where they land. Where the CDF is steep, a tall stretch of the vertical axis gets squeezed into a narrow band of x, so a great many samples pile into a small interval. Where the CDF is flat, the reverse. A long stretch of x picks up almost no vertical range and almost no samples. Steep means dense, flat means sparse. The slope of the CDF is the density, that is lesson 7, and this whole construction is that statement used backwards. Work it for the exponential. Its CDF is 1 minus e to the minus lambda x. Set that equal to u, solve for x, and you get x equals minus the natural log of 1 minus u, all over lambda. A single logarithm, and you have an exponential sample. Discrete targets are even easier. Stack the probabilities into cumulative bins along the interval from 0 to 1, then see which bin your uniform lands in. A loaded die, a categorical draw, a bootstrap resample. Every one of those is this picture. And now the catch. The method needs F inverse in a usable form, and a great many distributions simply do not have one. The normal is the famous case. Its CDF has no closed form at all, let alone an invertible one. For distributions like that, we need a different idea entirely. Inverse transform sampling. X equals F inverse of U turns a uniform number into a sample from any distribution whose CDF you can invert. Exact, one shot, and it never throws a sample away. It works because the CDF is precisely the function that maps your distribution onto a uniform scale, flat where probability is scarce, steep where it is dense. Next, what to do when you cannot invert F. Draw a shape you can already sample, throw darts underneath it, and keep only the ones that land below the density you actually wanted. Rejection sampling.